In the last video, we defined eigenvalues and eigenvectors. In this video, we want to actually go ahead and work out some problems of finding some eigenvalues for various matrices. Just work out some of the problems from the book. Now, the problems for this section are a little weird. Most of the problems are actually very proof-based, and you'll have a few proof-based type problems on your homework. We'll do a few of those as well. Most of the problems in this section that are just calculational, that are here's a matrix, find eigenvalues and eigenvectors, is all just pretty much in problem 1. And you're going to be working out 4 of these on your homework. You're going to do problem parts A, D, F, and K. So we'll work out a few of them. We'll go ahead and do problems B, C, G, I, and L. Or at least those are the ones I hope to go through. We'll see how much time we really have. So let's just start with B. 1B. We have our matrix 6, -4, 3, -1. We want to find out what are the eigenvalues of this matrix. So remember, what we need to look at is our characteristic equation. We're going to take the determinant of A minus lambda I. What does A minus lambda I do? Well, lambda I is just the identity matrix is just the matrix with all zeros except for ones along the diagonal. When we multiply it by lambda, we get a matrix of all zeros but with lambdas on the diagonal. And so we're basically subtracting from A lambda on each of the diagonal elements. And then we're going to look at the determinant of that. So that's all I'm going to do here, is I'm going to look at the determinant of this 2 by 2, but instead of our diagonal elements of 6 and -1, I'm going to replace them with 6 minus lambda and -1 minus lambda. And I just take the determinant like normal. So remember, take the product of 6 minus lambda and -1 minus lambda, then we subtract the product of -4 and 3. And then this is, because we're working with a 2 by 2 matrix, this is a quadratic. I guess the whole point is that we want to set that equal to 0, so eventually we're going to set this equal to 0, but let's actually simplify this formula. If we expand this out, well, we'll have a negative lambda times a negative lambda, we get a lambda squared. We have a negative lambda times -1, so a lambda, but then we also have a negative lambda times 6, so a -6 lambda. If we add those together, we get a -5 lambda. And then we have 6 times -1, so we get a -6, but we have the 12 outside. So 12 minus 6 gives us a positive 6. And we want to set that equal to 0. Now, of course, since we're not going to get into really complicated ones here, I can actually factor this one. Otherwise, we'd have to use something like the quadratic formula, which doesn't really work if we're dealing with the bigger matrices. So really solving for eigenvalues can get kind of messy in general, but we're going to have some nicer problems in this first problem at least. So how do we factor this one? Well, we need numbers that add to -5 but multiplied into 6. Well, those are -2 and -3. So our eigenvalues are 2 and 3. What are the corresponding eigenspaces? Or really, since the eigenspaces are the null spaces of A minus lambda I, then what we're looking for is a basis for those null spaces. We're looking for, as long as we can find eigenvectors corresponding to these eigenvalues, we'll be good. What do we need to do there? Well, remember, what we're doing is A minus lambda I. We're going to take each of these lambdas that we found and take this same matrix that we have here, but we're not taking the determinant of this time. So We'll have one where we have lambda equals 2. We're going to take 6 minus 2, so we get a 4. We have a negative 4. We saw this 3. Then we have negative 1 minus 2. And since these are eigenvalues, so we already showed that they're eigenvalues, this should have a non-zero solution to its null, a non-zero vector in its null space. Let me put it that way. So we can imagine having a column of all zeros here. I'm not going to write that because it's not going to change as we do any row operations. And I'm probably not going to write out every row operation as we go through these problems. So just remember how all that goes. But we can actually convert this. So the 4 and the negative 4, we can go ahead and divide that by 4. Then we can use that to cancel out this row. In fact, you should expect to have a row of all zeros if this is going to work out. And we're looking for any solution. You could say x and y, where x minus y is equal to 0. Well, y is a free variable. Let's just set it equal to 1. So we can have an eigenvector of 1, 1. And the eigenspace is going to be the span of that vector. So we could actually write that out if we wanted to. I'm just going to kind of write out a basis over here. Then we have to do the same thing for lambda 3, or lambda equal to 3. We do the same thing where this 3 and negative 4 are the same, but now we're going to be subtracting by 3 instead of subtracting by 2. So 6 minus 3 gives us a 3. Negative 1 minus 3 will give us a negative 4. Might feel like we're getting very similar things here and all that, but that's actually the whole point. The whole point is that this is something that is singular. It's a singular matrix. These rows are the same, so we have a singular matrix. Of course, if we do row operations, we can cancel out that row. The first row doesn't really simplify. Y here is our free variable. We can pick something for that y and solve for x. Since we know we have a 3 here, let's go ahead and pick 3 for y, so we don't have to deal with any fractions. And then if we solve for x, we get 4. So this is a basis for our null space for this matrix, which means that it is a basis for the eigenspace corresponding to 3. Now we'll move on to C. So here's our matrix. Just copied it over. We have 3, negative 1, 1, 1, and we do exactly the same thing. We'll look at the determinant of the matrix where we subtract lambda from each of our diagonal elements. We expand this out. So we have 3 minus lambda times 1 minus lambda, but then minus negative 1 times 1. So we have a plus 1. We go ahead and expand that out. We get lambda squared, because we have negative lambda times negative lambda. We have a negative lambda times 1 and a negative lambda times 3. If we add those together, we get negative 4 lambda. Then we'll also get a 3 from this, but we'll add 1 to that. So we get a 4. Of course, we can go ahead and factor this. This is lambda minus 2 squared. And we're looking at where is that equal to 0. Of course, that just leaves us with lambda equals 2. So in this case, we only have one eigenvalue. Now, that means that we could potentially get multiple eigenvectors spanning the eigenspace. That doesn't have to be true, and we'll actually talk about that a little bit more in 6.3. But for the moment, we're just trying to find out what are our possibilities. So we'll go ahead and take our matrix. So I guess this matrix here, but we're subtracting 2 from our diagonal elements. So 3 minus 2 is 1. So that negative 1, that 1. Then 1 minus 2 is a negative 1. Of course, we can do row operations here, cancel out that second row. And what do we end up getting here? Well, Here, x minus y is equal to 0. If we choose 1 for our y, we get an eigenvector of 1, 1. And if we pick anything else for y, all we're going to do is get another multiple of this same vector. So we actually only have one eigenvalue and only a one-dimensional eigenspace. Like I said, we'll see later in section 6.3 that can be kind of a problem. We actually have a term for this kind of a matrix where we don't get the same number of eigenvectors or independent eigenvectors as the size of our matrix. So this is 2 by 2. We would want to get two linear independent eigenvectors, and we didn't do that. Well, we're going to call a matrix like this defective. And we'll see why we use that very kind of insulting term for it later on. Why this is such a big problem for us in solving some of these problems. Now we'll move on to a 3 by 3 matrix. The process is similar, but of course it's going to be more calculations. So we're going to take our diagonal elements, subtract lambda, and leave everything else alone. And then we want to find the determinant of this. Now, this is actually a very nice matrix because it is upper triangular, and even when we subtract lambda from our diagonal elements, it still is upper triangular. Remember, we can find determinants of upper triangular matrices by just multiplying the diagonal elements. So we have lambda minus 1 times lambda minus 2 times lambda minus, the lambda's not first. 1 minus lambda times 2 minus lambda times 1 minus lambda. And we want that equal to 0. We don't have to expand it out because it's already factored for us. So what are the solutions? Well, of course, here lambda is 1 or 2 because we have the same factor in two places. Now, is this going to be defective like the last one? We'll have to see. That's not something you can easily see right off the bat. So let's let lambda equal 1 first, and then we'll work it out. We'll see what happens. All we need to do is subtract 1 from our diagonal elements. So here we get 0, 1, 1, 0, 2 minus 1 is 1. Then we solve 1. We have 0, 0, 1. Or not 1. 0, 0, 0. Of course, we go ahead and use our row operations. We can actually cancel out that second row in its entirety. So I have a very nice, well, nice in some sense, you might say, matrix here. And not only is z a free variable, but you can actually see that x is a free variable. There's no constraints on x. So what can we do here? We can get two eigenvalues, or sorry, eigenvectors. One where we keep let's let z equals 1, which is going to actually force y to be negative 1 because y plus z equals 0. But we'll let x be 0. So we'll call that x1. And another vector, this time we'll keep z equal to 0, which will force y to be 0 as well, but this time we're going to let x equal 1. Both of those are eigenvectors corresponding to 1, but they are independent of each other. The eigenspace is the span of these two vectors. So we actually do have a two-dimensional eigenspace for this one. For lambda equals 2, very similar. We're going to subtract 2 from each of our diagonal elements. We'll get negative 1, 1, 1. Get 0, 1, this should be 0, then 1, and then 0, 0, negative 1. We go ahead and simplify this. So we'll keep that middle row as it is. We'll use it to cancel out the 1 down here. We'll also use it to cancel out this 1, but we'll also multiply this first row by negative 1. So we're going to get this overall. So what does this mean? Well, the second row is telling us that z is equal to 0. The first row is telling us that x minus y is equal to 0, so x and y are equal. So we can actually use this to get a single eigenvector of 0 down here for z, but then 1 and 1 for x and y. So any other solution, any other eigenvector is going to be a multiple of this. We have a one-dimensional eigenspace for corresponding to 2. Now in I, this is actually probably one of the more complicated ones we're going to be doing here. We still have a 3 by 3, but it's not upper triangular this time. So we're going to have to do a little bit more work to actually find this one. So we're going to go ahead and do the same thing. We're taking our determinant. We subtract lambda from each of our diagonal elements. That also means that this 0, we're going to have 0 minus lambda, so do not forget to put that in there. So we actually lost a nice 0. But even this one is not as, you could say, as bad as it could be, because we do have this 0 down here. We can actually use that 0 to actually find out what this is. So we might say expand along this bottom row. So we have 1 here that we multiply by its cofactor. So we have a negative. Then we have this negative 4 minus lambda multiplied to this negative 1. We subtract that 1 times the 1. Then we add this term, so the negative 1 minus lambda times, now we're taking this one, so negative 4 minus lambda times negative lambda minus the negative 5 times the 1. So here, this is actually a good amount of actual expanding. I'm going to skip some of the steps here just for time. It is just algebra at this stage. What you'll get if you expand the entire thing out is minus lambda cubed plus 3 lambda squared minus 2 lambda. So obviously they set this up so we actually do have we have a 0 for our constant. That'll actually make it easier to factor this. I'm actually going to go ahead and pull out a negative lambda. So that's going to be now lambda squared minus 3 lambda plus 2. And then hopefully you can see that we can factor this. So we need two numbers that multiply to 2 but add to negative 3. Overall, we're going to get negative lambda times lambda minus 1 times lambda minus 2. So we have 3 eigenvalues here. And that's normally what's going to happen when you have a 3 by 3 matrix. So we have 0, 1, and 2 as our eigenvalues. Don't forget the 0. That's negative lambda out in front. It's not there for no reason. What this is actually saying, this lambda equals 0 being a solution, means that our matrix here is actually a singular matrix to begin with. Not obvious at first, but you can actually see why that might be, because the determinant here, remember the determinant was the constant for our characteristic polynomial. Our constant is actually 0. So this has determinant of 0. So we're going to find eigenvectors corresponding to each of these. So first we put in 0. Well, that actually just gives us our original matrix because we're subtracting 0 from the diagonal elements. And then we go through a bunch of row operations. What I actually did is I kept the second and third row as my first and second row. And then I use those to cancel out stuff in this first row. Of course, because everything's singular, we turn that to have all zeros there. And so what we can get here, if we use our free variable of z, set that equal to 1, then we have y is also going to be 1, and x is going to be 1. So our eigenspace corresponding to 0 is spanned by 1, 1, 1. If we look at 1, Now we're subtracting 1 from each of our diagonal elements, but leaving everything else alone. Go ahead and do all of our row operations again. Again, I put the second and third row as my first and second row. Actually, I'm not going to even touch that second row anymore. And we can actually use that second row to cancel out. Well, we can use both those rows to cancel out everything in our original first row, and then also use the second row to cancel out the -1 that we have here. So we actually get a 0 there, and we end up with a -3 there. So skipping over some steps here, but we've done a lot of row operations before. These are just the same ones that we've used before. But again, z is a free variable. I can pick it to be whatever I want. I'm going to pick it to be 1 because we don't really have to divide by anything when we solve for x and y. But that means that y is going to be equal to 2 and x is going to be equal to 3. So this is our, well, the eigenspace is the span of this vector. We have a one-dimensional eigenspace. Every vector is a multiple of this one. Then we go to 2. Subtracting 2 from each of our diagonal elements. So now we have -3 here. Everything else is the same. We do all of our row operations like we did before. Again, making use of those 1 and 1 to make this a lot easier for myself. And of course, as pretty much always, we're going to get a row of all zeros here. We should expect that. We'll still have that -3 from here, but again, I went ahead and cancel out that -2, and I end up with a -7. We end up with a basis for our eigenspace of 7, 3, 1. So this is kind of a typical example. Even this is a little bit simpler than how it could have been, but it's very typical of how these things actually behave. We usually expect to get different eigenvalues in different eigenvalues, and we expect to get one-dimensional eigenspaces. But that doesn't always work. But if it does happen that way, it's actually probably the best situation overall. Finally, we're going to go ahead and look at a 4x4 matrix and try to find eigenvalues for this one. So, of course, this would be a very more complicated problem than the last one, except that we do have a lot of zeros, and that's going to make things a lot nicer for us. But we still need to go ahead and set this up by subtracting lambda from each of our diagonal elements. And these are all the non-zero elements, but we kind of want to fill in the rest of it. And how do we take the determinant of this thing? Well, we just think about what we get if we expand along the rows. So we can expand along this first row. We have a 3 minus lambda times, I'm actually going to go ahead and write this one out just because it's kind of complicated. So it'll cancel out this first column and this first row and leave us with this 3x3. And actually, we're left with an upper triangular matrix. We can find the determinant of this 3x3 by multiplying the diagonal elements. So we have this 3 minus lambda times 1 minus lambda, and then we have two copies of 2 minus lambda. So actually, we're in a pretty good state here. We don't have to do any more expanding. So maybe looks more complicated than it really is just because of the very nice form for it. But we do have 3 eigenvalues, 3, 1, and 2. 2 is a repeated one. You can say it has a multiplicity of 2 because of the square. But that doesn't necessarily mean that it has a two-dimensional eigenspace. We'll have to see if it is defective like we had on that previous one. But we do the same thing. We look at all of our eigenvalues. Let's start with 3. we subtract 3 from each of our diagonal entries. So we have a -1 here, -1 here, -2 here. Do all of our row operations, which again, I might not go through all the steps of that, but it's not too bad. First of all, I'm going to move the row of all zeros down to the bottom. I don't really have to. Should have another 0 there. That should be further up. I'll go ahead and turn those into positive ones, but put them here, and then I'll go ahead and divide that by 2. So here, that means that our x4 is 0, our x3 is 0, but our x1 and x2 are related to each other. So we have 0 and 0 here. I could pick 1 here, but I'm going to go ahead and pick 2 to avoid fractions, and that will mean that our x1, has to be 1. So, a one-dimensional eigenspace. Now if we look at 1, we subtract. So we have 2 there. We saw all that similar. We get all the zeros in this column. We get zeros here and here. This becomes a 1. That becomes a 1. And we get that thing. Well, I'm going to keep this first row, but I'm going to divide it by 2. I'll use it to cancel out, well, in fact, cancel out this entire second row, which I'll go ahead and put as my 4th row. And then I'll go ahead and put my 4th row as my 3rd row, and use that to cancel out the extra 1 that we have in that one. So what is this telling us? This is telling us that x4 is 0, x3 is 0, x1 is 0, but it doesn't tell us anything about x2. So x2 can be whatever it wants to be. We'll just let it equal 1, but the point here is that this is a basis for the eigenspace. The eigenspace is all the vectors where everything is 0 except for possibly x2, which can be whatever it wants to be. What about lambda equals 2? So what do we have? We have a 1 here, a -1 here. We have a 0 and a 0 there. Lots more zeros. We still have a 1 here. Sorry, this looks a little sloppy. But we have this row of all zeros on the bottom. Guess we go ahead and keep this row as it is. We still have this first row as it is. And then I'm going to go ahead and use this 1 to cancel out the 4 there, but eventually we can actually simplify this down to 0, 1, 0, 0. And then this is very similar to lambda equals 1, except now we have the 1 here instead of here. But that means that our x1, our x2, and our x4 are all zeros, and then x3 can be whatever it wants to be. But we only got one vector here. Even though we had a square here, even though we could say it's a multiplicity of 2, we only got a single basis vector. So this is another example of a defective matrix. Technically, that term is not defined until 6.3, but I do want to emphasize in all these examples when that happens. All right, so this is good examples of how to find these eigenvalues, how to find the corresponding eigenspaces. This will be very important when we get to 6.3. I'll go ahead and do some more problems in another video, but they're going to be more of the proof type problems that you'll be seeing. You'll be working on your homework. You'll be working on, I think it was 10 and 26. Yeah, but I'll be working a few of the other ones. So I'll see you in that video.